Hello students, let us discuss on polar curves. Before discussing on polar curves, let us recapitulate functions of single variable. The concept of functions is important in calculus because they play a key role in describing the real world problems in mathematical terms. For example, the temperature at which water boils depends on the elevation above sea level. Here, the temperature is a function of elevation. The interest paid on a cash investment depends on the length of time the investment is held. Here, the interest is the function of time. The area of a circle depends on the radius of the circle. Here, the area of circle is a function of radius of the circle. A symbolic way to represent y as a function of x is by writing y equal to f of x. In this notation, the symbol f represents the function. The letter x is called independent variable, which represents the input value of f, and y, the dependent variable, which represents the corresponding output value of x. Why the requirement of new coordinate system? The requirement to define any new coordinate system is twofold. One is based on geometry of the problem of practical situation, wherein a more suitable coordinate system has to be chosen. The second requirement is more of theoretical in nature. Mathematical expression which cannot be simplified in one coordinate system may be solved in simple way by transforming to other coordinate systems. Let us discuss on basics of polar coordinates and polar curves. Any point P can be located on a plane with coordinates r and theta called polar coordinates of P. Here P or theta is the polar coordinate of the point P, where r is the radius vector OP, which represents the distance OP, the distance from the origin to the point P. Theta, the projection of OP on the initial line OE. The equation theta equal to f of r or f of r theta equal to c, known as polar curve. Let us discuss some applications of polar curves. The practical use of polar curves is to describe directional microphone pickup patterns. A directional microphone will pick up different qualities of sound depending on what location the sound comes from outside of the microphone. Also, the calculations involving aircraft navigation, sea navigation, gravitational fields and radio antenna are applications in which polar coordinates are used. Polar coordinates can be very useful in anything involving rotation. Let us see what is the relation between Cartesian and polar coordinates. Let xy be the Cartesian coordinates of the point P. Then r equal to root of x square plus y square, theta equal to tan inverse y by x is the transformation equation to transform the Cartesian coordinates to polar coordinates r and theta. Taking the inverse transformation, x equal to r cos theta, y equal to r sin theta are the transformation equations to transform the polar coordinates to Cartesian coordinates. So we can say that the relations 1 define the transformation from the Cartesian coordinates to polar coordinates, and relation 2 defines the inverse transformation. Let us find angle between radius vector and tangent. Let phi be the angle between the radius vector OPL, and the tangent TPU at the point P on the polar curve r equal to f of theta. Then angle between the radius vector OPL and the tangent TPU can be obtained by using the expression tan phi is equal to r d theta by dr, or the other way cot phi is equal to 1 over r dr by d theta. If phi1 and phi2 are the angles between the radius vector and tangents at the point of intersection of two curves r equal to f1 theta and r equal to f2 theta, then the angle of intersection of the curves is given by modulus of phi1 minus phi2. Suppose we are not able to obtain phi1 and phi2 explicitly, then using tan phi1 minus phi2 is equal to tan phi1 minus tan phi2 upon 1 plus tan phi1 into tan phi2, we can obtain the angle of intersection. If tan phi1 into tan phi2 is minus 1, then modulus of phi1 minus phi2 is pi by 2. So this can be considered as the condition for the orthogonality of two polar curves. Some examples. Find the angle between the radius vector and tangent to the curve r equal to a into 1 plus cos theta. R equal to a into 1 plus cos theta is of this shape. So this is of heart shape. So this curve is called as cardioid. Consider the equation r equal to a into 1 plus cos theta. Differentiating with respect to theta, both sides, dr by d theta is equal to minus a sin theta. Taking reciprocal and multiplying by r, both sides, r d theta by dr equal to a into 1 plus cos theta upon minus a sin theta. We all know that r d theta by dr represents tan phi. So tan phi equal to, from the trigonometric expressions, 1 plus cos theta is 2 cos square theta by 2 and sin theta is 2 sin theta by 2 cos theta by 2. So cancelling a will get minus cot theta by 2. Representing minus cot theta by 2 in terms of tan, we have tan pi by 2 plus theta by 2. So finally we get phi is equal to pi by 2 plus theta by 2. Another example is, find the angle between the curves r equal to a theta by 1 plus theta and r equal to a by 1 plus theta square. Consider the curve r equal to a theta by 1 plus theta. Let us take log both sides. We all know that log a by b is equal to log a minus log b. So taking log both sides, log r equal to log a theta minus log 1 plus theta. Differentiating with respect to theta both sides, 1 over r dr by d theta is equal to a by a theta minus 1 by 1 plus theta. Cancelling a from this expression and simplifying 1 by theta minus 1 by 1 plus theta, which gives 1 by theta into 1 plus theta. Taking the reciprocal both sides, r d theta by dr is theta into 1 plus theta. So tan phi 1 is equal to theta into 1 plus theta. Let us consider the other curve r equal to a by 1 plus theta square. Taking log both sides, log r equal to log a minus log of 1 plus theta square. We know that derivative of log a is 0, derivative of log of 1 plus theta square is 1 over 1 plus theta square. Again differentiating 1 plus theta square, it is 2 theta. And derivative of log r is 1 over r dr by d theta. So we get 1 over r dr by d theta is equal to minus 2 theta upon 1 plus theta square, which gives cot phi 2 is equal to minus 2 theta by 1 plus theta square. Taking reciprocal both sides, tan phi 2 equal to 1 plus theta square upon minus 2 theta. Eliminating theta between the curves, r equal to a theta by 1 plus theta and r equal to a by 1 plus theta square. Since LHS is same, equating the RHS and simplifying, theta cube equal to 1. And finally we get theta equal to 1. On substituting theta equal to 1 in the expression tan phi 1 and tan phi 2, we get tan of phi 1 minus phi 2 using the formula as earlier discussed. Tan phi 1 minus phi 2 is equal to tan phi 1 minus tan phi 2 upon 1 plus tan phi 1 into tan phi 2. We get modulus of 2 minus of minus 1 upon 1 plus minus 2, which gives modulus of phi 1 minus phi 2 is equal to modulus of tan inverse of minus 3. Finally it is tan inverse of 3. Thank you students.